short. I have no code to show you guys.
Ooh, sweet.
Oh, well, we'll see how it goes. So yeah, I want you guys to kind of discuss the concept. I need you guys to ask questions. In my mind, I think I know these things. So if I explain these things to you and you guys don't understand them, you don't tell me, I'm gonna assume you understood it, right? Now, just one more thing before we start. So, how many of you guys are web developers? How many of you guys are software engineers? Okay, let me rephrase that. How many of you guys are working towards becoming web developers? Okay, I see more hands now. God, guys, come on. Okay, perfect. Okay, wonderful. So as web developers, you normally don't run into these things because they're taken care of for you through the language, right? But it's wonderful for us to actually know what these things are doing because you'll start feeling smarter. So that's wonderful, right? And then in case you're asked in an interview, you have an advantage now, right? Because you actually know what's going on.
And there are reasons, I mean, specifically to write your own. Granted, Quicksort from the collections library is nice and whatever, but there's, especially when you're dealing with big chunks of data for customers and stuff, you will run into reasons why binary search is more useful than something else.
So you normally don't have this problem, but can you be louder?
Oh,
I can barely hear you.
pay attention, he's going to tell you everything.
No. Okay, so common sorting algorithms, right? Learning the common sorting algorithms is a great way to boost your performance. And again, because I forgot to mention this, but if you guys didn't see the first picture, it's from a book. All this information is from a book called Cracking the Coding Interview. How many of you guys have heard about that book before? Okay, wonderful. So just in case I lied to you guys, it wasn't me. So learning the common sorting algorithms is a great way to boost your performance. Of the 5 algorithms explained below, merge sort, quicksort, and bucket sort are the most commonly used in interviews. Okay? Let's not notice that I didn't put it right next here. So bubble sort. How many of you guys have heard of bubble sort before? Okay. I have not heard about it before. So in bubble sort, we start at the beginning of the array and swap the first 2 elements if the first is greater than the second. We have images coming right now, okay? I don't want you guys worried. So again, in bubble sort, we start at the beginning of an array and swap the first 2 elements if the first is greater than the second. Then we go to the next pair and so on, continuously making sweeps of the array until it's sorted. So it keeps going through the array, right? In doing so, the smaller items slowly bubble up to the beginning of the list, okay? So the whole point of doing this is sorting, right? We're pushing up the smallest item in the array, right? So let's...
Probably also the easiest to write yourself, by the way, as well. If you need like a quick demo or whatever, this one's easy peasy.
Okay, so can you guys see my mouse on there? Oh, you can? Cool, perfect. So you guys see this one right here at the top? Yes? No?
Yes.
Yes.
We're all tired from work. Okay, cool. Okay, so in the first sweep, you can see right here, there's no swapping, right? 11 is shorter, it's smaller than 17, right? What about the next sweep? Is 17 smaller than 18?
No.
Yes.
God damn it, Fess. You threw me off. I'm like, wait, what? I don't know my numbers. Okay, what about 18 and 26? Is 18 smaller than 26?
Yes.
Yes.
Perfect. Oh, because we know that. We're all answering, right?
Yeah.
Wonderful. Okay, what about 26 and 23?
Wow.
Okay, so because 26 is bigger than 23, we swap them, right?
Mm-hmm.
And now we're done because it's sorted, right? Was that complicated?
Nope.
So now you guys understand bubble sorting.
Yep.
Is there another slide?
Here. No.
Okay, because the complicated factor is that if it goes through and then it makes, like, let's say the 17-18 swap, then it goes through, it has to go back again.
Yeah, so it'll stop once it doesn't do any
It just
swapping.
keeps going until it gets to a
Until
zero
it's not
swap.
swapping anymore.
Bubble
Which
sort
is
is
why
in a
it's
while
not
loop.
very.
I'm sorry?
Bubble sort is in a while loop.
It depends
and that
on the
while
language,
loop
right?
runs until
Yeah, the idea is to, because you can actually do it in the for loop if you just hop your index.
yeah.
Because I know, for example, in JavaScript, because I use JavaScript, we have the sort method, and you can pass it in a function, and you can check the current value and the previous value. You can check if it's one smaller than the other one or greater, whatever you want to do, right? But that's essentially the same concept.
So I guess my question becomes then, that's, if I remember correctly, it's not considered to be a very, efficient.
No,
It's the
it
least
actually has
efficient.
the, O factors of the.
Yeah, so
slide,
the
yeah.
Yeah,
book.
oh, okay, and two.
Yeah.
Yeah, bubble sort sucks. It's just, very easy to write.
Yeah, right.
Wait, is that O n squared, or is that just?
No, all of n squared, yeah.
How would it be O n squared?
I'm sorry?
How would it be O n squared?
Cause the
Yeah,
worst case is that every single one of them has to be swapped.
Oh, because it has like a nested four-element array?
Oh, I thought you were asking why it's at the bottom and not at the top.
It has
Well, thank you
it
for
has
being
a form
specific.
that scans through the entire array, it just runs until the array is sorted.
It would be really fast if it was already sorted, right?
Right.
Cause it would just go
Go
down
through
to carry
once.
one, but
I think
if
I
every one
remember
was
that.
up,
I did.
yeah, you're literally swapping every one.
I'm waiting for like me
And
forgetting to put an image in
worse,
there.
if it, depending on how many swaps it needs, it actually, you might swap it and then have
I've
to go
gotta
back
wait
and
until
swap
it's
the
more
next
each.
one. Yeah. You could have to run through that entire array for every element in.
Okay, so we also have selection sort. How many of you guys have used that one before? Okay, so now we're learning. Wonderful. So the whole point of this one is to find the smallest element using a linear scan and move it to the front, swapping it with the front element. Then find the second smallest and move it. Again, doing a linear scan. Continue doing this until all the elements are in place. Do we understand that? So we're looking for the smallest item in the array, bring it to the front, right? And we keep doing that over and over again. Does that make sense?
Yes.
Okay. So we have an image. Okay, wonderful. So can someone tell me what's going on in the first suite?
It's establishing the
Yeah, it
first
found
one.
13, which is the smallest one in the whole thing, and swapped it to number,
Perfect.
Swaps it with
So it's
position
swapping,
one.
29 took 13 spot and 13
Yes.
went to the, yeah.
It's actually checking by position, so it's comparing the value of that position in the array. So position one's value is 29, and it holds 29 in memory as it checks the value in each other position in the array. And then it swaps position 1 and 4, because in position 4, 13 is less than 29.
Right?
Not less than, it's 13 is the smallest one in the entire array.
Correct.
That's why you move to 1, and then you find the next one, and you move it to 2, and you find the next
Well,
one.
but it swaps it when it gets to it, and then it just continues.
So
through
don't
the rest
don't
of the array.
overcomplicate it for yourself,
Well,
Scott.
I think what's confusing, Scott, is that 29 is the next smallest number, so it looks like it stayed on the same index, because it did.
Oh, this right here? Yeah.
Yeah, it's not, it's the second most completely
That's why I say
inefficient.
some of these, they didn't make these real
So
clear.
Well,
you see this right here? So for every swap, it's looking for the smallest number, right? So right here, it finds that 13 is the smallest number. Okay? When it goes into the second swap, okay, it finds that 29 is the next smallest
It has
number.
to go through the entire array
Yeah.
to do so.
yeah.
And it'll keep doing that until it's all sorted. Does that make sense?
Yes.
Let's see.
So it all made sense, right?
Yes.
So you guys learned selection, sorting. Wonderful. Oh, just in case you guys couldn't see.
I was saying like a good demo would be if you go to visual algo, it like shows it step by step how it's done.
So I do have some challenges for you guys at the end.
Oh, boy.
So it's not that easy. So, question, someone? Okay. Amber, you got a question?
No,
Oh.
sorry, I'm distracted.
I want you to know that he sold you out, right there, next to you. He pointed at you. Okay, merge sort. How many of you guys have heard of that one before? Wonderful, okay. Okay, so merge sort divides the array in half, sorts each of those halves, and then merges them back together. Okay? To how many did that make sense?
This one actually can be interestingly implemented if you start using multi-core and threads,
Mhm.
because you can actually throw out each one of those.
It'd be
splits
faster,
to-
yeah.
Yeah, so that way you can actually literally parallel process the different, depending on how many cores you got. Say you had 4 cores, you could split into 4 parts to start doing your sorting.
So all of that will make more sense once you guys see the image, hopefully, okay?
Okay.
So again, each of those halves has the same sorting algorithm applied to it. Eventually, you're merging just 2 single element arrays. It is the merge part that does all the heavy lifting, okay? Okay, so I found this image online. Okay, I didn't make this image. In case we find a mistake. Okay, so how does merge sort algorithm actually work internally, right? So it divides the array into two parts. So initially this is one array, right? Now it's divided into two parts. Part one, part two. Okay? Now, second step. It divides the array into two parts again, right? So part one, two, 1, 2. Okay, does that make sense so far?
Yep.
Okay, then it breaks each element into single parts. Okay, it sorts the elements from smallest to largest. Then it merges the divided sorted arrays together, and then the array has been sorted. Now keep in mind that this, if we go back, that says each of those halves has the same sorting algorithm applied to it, right? So that means that, what do you think is happening right here? Let me go point at this. So whatever's happening to this one, same thing's going on here, right? In terms of sorting, right? So notice how here we break it out into two, and then between these two, we're saying which one's smaller, right? And we're sorting it. And then at the end, we merge them, and then we end up with two, we merge them, and now it's sorted. Does that make sense?
I'm missing the between 5 and 6, because when you put them together, they're each individually, they're
Where is
sorted,
it?
but then if you put them together, they wouldn't
Yeah.
be.
You want to point that out to me?
The
Where is
last,
it?
second to last.
On number 5, merge the divided sorted arrays
Here?
together. Yeah, so if you stack that together, 43, 9, and 10 are smaller than 43, so how did they suddenly jump into position?
What it does is, it compares 3 and then 9, and then it puts 3 in, and then it compares 27 to 9, and then it puts 9 in, 38 to 10,
Yeah.
it puts 10 in, and it keeps going like that.
Merge the divided sorted arrays together.
And it
Again,
does-
I didn't create this image.
It does-
No,
So-
I know, I guess that's.
So Vass, you want to
It's always
explain
been
what
the
the hell's
thing
going on over here?
that's-
No, he's right, he's totally right. If you think about each one of the steps from 3 down, it's doing the same thing to get the next chunk of elements, right? 27, 38, so when it goes to the next one, it puts 27 first and 38 second.
So we're missing
3 and 43
5
goes
and
down,
6.
right? So then when 27, 38 and 348 go down, it sorts them there. And
Oh,
then
okay.
of course down to the next one as well. So you do that until you have no more chunks, and voila, you have your sorted array. This is not this is a fairly quick,
So between those three that we just went over, which one's fastest?
this one.
This one? Okay.
Well,
Because
I
you're
mean,
doing them-
in best case, right? Like in best case, then the other one would be quick because they're like.
But the reason it's quick is because you're doing two things at the same time, right?
Sort of that you're doing two things
Okay.
at the same time. Yeah, sort of. You don't have to. The thing with this one is you don't have to go through the array over and over again.
That's where it starts
Right? You
sorting.
split it out, and now you
Sorts
have the
with each
two
step
arrays that you're
till
dealing
the
with, and
last
then you
one.
split that out. So
It
you're
just
not
keeps
going
sorting.
through that
Okay.
array, in
From
times to
step
find
4 to
out the
step
smallest
5,
one
keep
is.
sorting
Take a
there.
lot more
Okay.
memory.
So does this one make sense?
Because you have to have all
No,
those arrays.
Because all those are actually,
Yeah.
you don't create
27
new arrays
it
for each
goes
one
in
of those.
pairs.
It's all
Okay.
just in there.
Okay.
Kind of
So
puts them
instead of,
together and
like,
then
yeah, I mean,
sorts
it's like a
them.
If you just-
virtual one, but it's really just saying index 0 to 4,
Then
and
27
index
with
0 to
48,
1.
then 38 with 40.
Just swap the pointer instead of the.
I like how Scott's always asking about like what's going on in memory. We just think it's magic and it's fine.
Right, whenever you get, if you contribute, now, I will say you have, there's a tiny bit of overhead because you have to essentially figure out how many quarters not only you have, but have available. But then if you do sort them on each one of the things, it gets.
I'm just waiting for
When
Vass
you're
to
doing
be
true
done.
parallel processing, right,
Okay, so Quicksort. Quicksort is a divide and conquer algorithm. It creates two empty arrays to hold elements less than the pivot value and elements greater than the pivot value, and then recursively sort the subarrays. There are two basic operations in the algorithm: swapping items in place and partitioning a section of the array. Okay, so let's look at the image. So, correct me if I'm wrong, Beth, but the element that it utilizes to pivot, it's chosen at random, right?
It is, that's why Quicksort is not usually used if you need, predictable, sort times.
Okay.
Right, because it does have the randomness factor to it.
And what
It is used often because when it's fast, it's really fast. When it's not really fast, it's still okay. So it's used quite often because you can get very quick results.
Now, if I understand correctly, what it does, you have two different arrays, right? Anything that is smaller than 5, it'll put on the left one.
Mhm.
Anything greater than 5, it'll put on the right side, right? So you can see, yeah, it's too small. Let me.
That's,
Sound like a binary tree would work?
That's
no, binary searches.
Some of the
Oh,
things
I
he
think we
says.
talked about that. Really.
Okay. So this first pass here, the initial array where the pivot hasn't marked. So randomly, we've chosen 5, right? So the first 2 elements are each compared with the pivot, and they're swapped with themselves. The next 2 elements are greater than the pivot, so they remain where they are. Here, the 2 is smaller than the pivot, so it is swapped with the first element available. And then 7 is larger, so it remains where it is. And finally, the pivot swapped into the correct location. The array has not been partitioned, and the index of the pivot can be returned. Okay, so did we understand the important concept though? That we have the array, we have a pivot that's chosen at random, and then anything that's smaller than that item chosen goes to the left. Anything greater than that goes to the right. Does that make sense?
See,
But does it put it to the right or to the left in descending order, or?
Not
yeah,
part of that
because it does
picture.
the comparison.
Okay.
So that's why, like, if
So
it's on.
So for, let's see, for example, second to last one.
This one was smaller.
This one?
Because you're actually three different arrays.
Yeah,
It takes first 7, and then it puts it, no, first takes 8, and puts it on the right, and then it takes 9, and then it checks 5. 8 is not less than 9, so then it puts it on after the 8, and then the 7 it checks for 5, then 8, and then 9, and it sees that 9 is greater, so it puts it in between.
So what I would do, because I have a hard time understanding things, is it says there's 2 empty arrays, right? Everything that's less than 5 is on the left. Everything that's greater than 5 on the right.
Oh, but
And
it's not
as
sorted yet.
yeah,
It's not.
but think about it this way. This is the pivot, right? So as you're finding things that are smaller, it's putting them into this one, right? As it's finding things that are greater, it's putting it into this one, right? So this one's in the middle, and the left side sorted and the right side sorted, right? Does that make sense?
Yeah.
Or did I not explain it correctly?
Yeah, and then it would just pick a new pivot point and start over until it got everything.
Right.
That's what I was gonna say.
Okay.
Like, it'll
That's
start, it'll pick the 3, and then it'll put the 2 over it.
Right.
Or on the left side of it. And then 3 will be sorted, and then it'll just pick the 2, and then it'll put the 1, they'll be sorted. And then it'll
No, it's actually fast. Yeah, you go do some of the, you can watch visualize it too. I mean, yeah, it's actually.
Is the one that you mentioned, heap sort, is that faster?
Heap sort, well, heap sort is good just simply because it utilizes like extra memory, so that's why it can be quite good, and it is the great thing about it is it pretty much always takes exactly the same sort time. So that's why it's used. It was mentioned, I think C++ uses it as its default sort. Quite a few languages actually use Quicksort as their default, just because it is really fast most of the time.
Okay.
But yeah.
Okay, this one, I'm gonna explain what I think happened, okay, and then we can figure out what happened. So let us figure this one out though. Just don't let us drown. So, Radixsort is a sorting algorithm for integers and some other data types that takes advantage of the fact that integers have a finite number of bits. In Radixsort, we iterate through each digit of the number, grouping numbers by each digit, okay? Yeah, so it's only this. So, okay. So what I understood happened here, hoping Vasa Smile is not.
Alright, this is all nerd
It's in the
stuff.
book. We've
Nobody
gotta,
does this.
but it's interesting to know. Point is, we go through each digit, right? So we sort it by the first digit. So, right? And then we sort it by the second digit, and then so on. Am I incorrect, Vest?
No, it's correct.
Okay, perfect. I've never
just-
seen this used, but
Yeah. Well, it's just like, some people do their swaps as opposed to creating a temporary variable and just do it. I mean, they'll use the bit shifting to so that you don't actually have a shift of, but again,
I mean, it's there.
You want to talk about a nano optimization? Come on, it's
now, do you think this would be brought up in an interview?
maybe, but if they ask me, I'd just be like, yeah, nobody uses that. Let's
Oh.
get on to making some stuff.
Well, there you go. Go with his recommendation.
I'm just calling him a nerd and go on to the next interview.
But before we move forward, we understood that we're sorting by digits first, right?
Yes.
And then the second one, and then the third one, right? Did that make sense? I should probably use better words. Okay. Okay. There's one search algorithm in the book, and then there's like a note about it. Okay?
Really?
Yeah.
Binary search?
Yeah.
Oh,
But
binary search is wonderful.
no. What I say about note is like don't limit yourself to just binary search,
Oh.
because then we're also going to cover trees and graphs
Oh.
in a separate talk. So in computer science, binary search, I wasn't talking anything about. I don't even know what it is. Also known as half interval search. I can't say that word. Can someone?
Logarithm.
Okay, that right there, search. I'm not even gonna try. So, or binary chop. I like that one better. Is a search algorithm that finds the position of target value within a sorted array. Now keep that in mind. It's a sorted array already,
Right.
right? Binary search compares the target value to the middle element of the array. Okay, so let's try that. Okay, one more explanation. In binary search, we look for an element x in the sorted array by first comparing x to the midpoint of the array. If x is less than the midpoint, then we search the left half of the array. If x is greater than the midpoint, then we search the right half of the array. So just right there, you can kind of tell that you're saving a lot of time, right?
Enormous. A million elements is in 20 checks.
Because if you think about it, you're
20 checks.
you're
Because
taking
it cuts
half
it
of
half
that
every
array,
time.
and you don't have to search
Yeah,
through it
it's-
anymore.
This
And
is,
then you take half of that and half of that and half
Right.
of that.
So we then repeat this process, treating the left and right halves as subarrays. Again, we compare x to the midpoint of this subarray, and then search either if it's left or right side. We repeat this process until we either find x or the subarray has size 0. So an example. Is this making sense? Okay, because I was so surprised when it made sense to me.
it's interesting to me that you are demoing this in an array thing as opposed, most of the time you see this in like a binary tree. Because that's easy to cut off half and cut off half and cut off half, whatever.
You don't
All
want
right,
me to
let's
do it, it's fine.
No, man, that's how you.
I don't even like talking about anxiety over
That
here.
thing's got pretty colors and everything.
I'm all fighting it. You're telling me it's fine. I can sit down. So step 1. Okay. So what are we doing in step 1? You guys all said you
You
understood.
look,
What do you
you
do?
find the midpoint
You
of
find
the
the
array.
midpoint.
Okay, perfect. Well, you tell me that. Don't just look at me like I told you a joke that wasn't
I'm
funny.
always talking.
Okay, well. Okay, so we look at the midpoint, right? And what do we do when we look at the midpoint?
Compare it to your value.
Okay?
To see if it's what you're looking for.
So what
It's interesting to me though, because you're talking about a search algorithm here as opposed to everything before was not. That was a sort algorithm.
Right. So
Yeah,
So
we've
we've
gone on.
pivoted over to
right.
that.
We've
But
gone
again,
on
the
to
chapter
part
talks
two.
about sort
Sorting and
algorithms
searching.
and search
I see.
algorithms, right? And it only covers one search algorithm, right?
They covered the good ones though.
Does
But-
it pick,
Yes.
does it pick middle by the middle like
No,
value
link
or the
divided by
index?
2, and
Oh.
because it's an integer, it'll tell you a whole number as opposed to 0.5.
So what he said, I was going to say that exactly.
So it's assuming it's already sorted.
I'm sorry?
It
Yes,
just works based
yes.
on that it's already sorted.
It's already sorted. So I think that's why they covered sorting first.
Right.
So then we understood this, right?
Yeah.
Mhm.
Okay.
Is 13 the number I'm looking for? No. Is it higher or lower?
Perfect.
Right, and then you get everything, because you cut off the first half of the array.
I actually
So now
remember
you-
the Harvard's online CS50 he uses a phone book. And it's
Oh.
really because he actually tears it in half. He's like,
What?
if you're looking for Roberts, you open it up to the middle. Is Roberts on
He
this
tears
page?
it in
No.
half, the phone book? That thing's
Yeah.
buff.
Okay, yeah, it's a little one.
It's a little one.
But it kind of solidifies the concept
It's showing
of
us- it's showing you
you
something
rip it in
else.
in half, you throw this half away because you don't need it.
It's still pretty.
So the book does have a quick note. It says potential ways to search a data structure extend beyond binary search. And you would do best not to limit yourself
You've got to
to
spread
just
it,
that
and you
option,
get it to 10.
right? You might, for example, search for a node by leveraging a binary tree or by using a hash table. We covered hash tables in a prior talk.
Yeah.
We're going to cover binary trees and graphs.
Sweet.
Not today.
No.
Enough anxiety for today. Think beyond binary search. That's what the book says. Okay? Now, we do have 3 challenges in the
Oh, boy.
presentation. You can find them online all over the place. What is it? LeetCode has
LeetCode.
them, HackerRank has them. These are links to HackerRank. Signal Code has them. But the cool thing is that you can actually apply what you just learned or you already knew and just reviewing and see if you actually know what you're talking about now. Okay? So we have Quicksort, BubbleSort, and MergeSort. Okay? You
Did
guys?
the book is the one that pointed to
Come
that
on.
hacker rank thing?
No, it didn't. That
Oh,
was
you
all
did.
me.
Why? Why hacker rank?
Because it was easy. Look, how about this? After I'm done
You
talking,
already have accounts at Hacker Rank.
after I'm done talking, you guys network, you work on your projects, open workspace, and then he can bug you about, what is it? Blazor?
Oh,
And
I'd be happy to talk
about
Blazor.
LeetCode, okay?
Yes.
Oh, wonderful, perfect, okay.
Yay!
Well, thank you very much, guys.